So now that we have seen a little bit about how multiple files can be used in order to organize your functions, and I can call functions in one file from another file, it is also useful to understand a little bit more about the compilation process itself, so that we are sure that we actually know what's going on out here, right. Now the process of compilation is something that is well worth paying attention to if you are planning to write any non-trivial amounts of C code, right. And what actually happens over here is you need to keep in mind what the compiler is supposed to do, right. The computer by itself only knows how to execute machine instructions, whereas what we are writing is text effectively, right. I mean, we can call it a program, but it's a bunch of ASCII characters in a text file. So what the compiler does is it basically takes this source code, which could be in several different C files, and each one of those is compiled, right. And the important thing to keep in mind is this compilation step only takes C source code and generates machine code. It does not by itself create an executable file, which means that each of these .c files gets converted into a .o file separately, okay. Now once I have that, I have a number of different .o files, each one of which contains different functions. Some of them may contain variables that need to be accessed by different functions, basically either globals or externs or static or something like that. And I need to put all of that together and create an executable. I might also find that I am trying to use some kind of standard libraries, things like printf, scanf, square root and so on, okay. I need to put all of this together. That is done by the linker, which basically combines different libraries, which incidentally could also have been started out in different languages, right. And it allocates relative addresses, it puts everything together and creates something that can actually run as an executable. Now there are two ways by which I could do this. One of them is explicitly do each compilation step on my own, right, which is that the first step, which is compilation from a hello.c file into a hello.o file, is usually run by running a command something like this, gcc, which is the GNU C compiler, with a -c option which says only compile, do not try and create an executable. What that does is it takes the .c and creates a .o file. And the next step, we take a shortcut and just say gcc hello.o. In reality, it is not exactly gcc that is doing the work over here. It's another program called ld, the loader, right, the linker and loader. And what that linker does is that it takes the code in hello.o. It also takes some other code corresponding to something called the standard C runtime library and puts both of them together and creates an executable file. If I do not specify the name of that executable file, it will create a file called a.out, but if I do give with a -o option again, I might end up getting a file called hello instead. So the simple way that we could use is basically to collect a bunch of these different commands together into a single script, something that we might call a shell script, and execute them sequentially, right. So let's take an example of that. So in order to understand exactly how the compilation process is working, we need to go to the shell, because if we just click on the big run button out there, Replit does some magic behind the scenes and gives us a compiled executable, whereas we are trying to understand how it works in the first place. So let's go take a look at the files, and if you look, you will notice that there is this file I have created which goes by the name comp.sh. And the reason I am calling it a .sh file is because I have a bunch of commands out here, each of which I could have directly typed into the shell, and therefore for all practical purposes this is what I would call a shell script, right. In reality it's just a collection of commands, right, but the way that I put it together, it becomes a shell script. And if you look at it, basically what it says is first compile arith.c. So let me in fact go there and try doing this explicitly, right. I am going to clean this up, remove all the .o files that I have out here, and then go in there and rather than typing make, I am going to type in this command gcc -c arith.c, and it takes a small fraction of a second, and when I look for the file, it basically has created a new file called arith.o, right, that is the most recent file that got created. you can see that it has some size of 2 kilobytes, right, 2000 something bytes, whereas the actual arith.c itself was only 390 bytes. So why does arith.o look so big? Well, I don't know, but the point is that there is no connection between the size, not no connection, but there is not a direct relationship between the .o file and the size of the .c file. What it does depend on are the number of different functions, the parameters, the complexity of the function and so on. So in general, if you have a large .c file, you can expect to see a large .o file, but it's not just some multiplicative factor that relates the two. The point is we have an arith.o. I can do the same thing with main.c, and I find that now main.o has been created, which is even larger, right? It's like 6 kilobytes in size. Now what do? I want to put both of these together, and if I say gcc main.o and arith.o, right, I find that I get an error. And what is the error? It basically says undefined reference to square root, sqrt, the function, right? And of course I am using the square root function somewhere inside that quad1 function in arith.c. So what happened? How do I solve this? It turns out that the square root function is not part of the C standard library, it is part of something called the math library, and I need to explicitly include that. How do I do that? I could basically call gcc with a -lm. The -l stands for include this library, and m is a shortcut for the math library. It's such a common library that it just requires that one letter to indicate it. Sure, that worked. And what you can see is it actually created a file called a.out, right? And if I now try to run a.out, which I give it the path and say /a.out, sure enough, it ran exactly the way that my original main was running. I could also have changed that gcc command to give it a name. I could have called it main instead, right? And then if I run main, that works, right? I could have called it ABC, and well, ABC will work. It doesn't really care what the name of the output file is, right? You can just use anything that you want. So as we can see, what has ended up happening is I wrote 3 separate commands, gcc, this, and link both together. What I have done in this shell script is I have put all 3 of them together into one file. How do I run this? Usually I could do something like this, bash comp.sh, which basically says call a shell and tell it to execute these commands. And it went ahead, it ran everything, it didn't print anything out because that's how shell scripts work. It doesn't print anything out unless you explicitly ask it to. But at the end of the day, you will find that this main is the most recently created file, which got created as a result of running this comp.sh. In the process, it actually also compiled arith.o and main.o once again and created all of those files once more. Okay, so far so good. So in other words, this is definitely one way by which we can compile across multiple different files. So we have seen an example of how we could collect the commands required to compile into a single file and execute them sequentially. The problem is that for large projects, which can typically have thousands of files, each of which is thousands of lines of code, which net result being that you have millions of lines of code in your project, you are probably going to struggle with this, right? Because every time you make a change in one of those 1000 files and then run the script, it's going to try and run all of those 1000 compilations once again, whereas 999 of them did not change. So why are we really doing this, right? So to get around this, we try and do something called incremental compilation, right? And the way that incremental compilation works is, you recall the .o files that were generated by compiling each of the individual .c files. We keep them around, right, until they change. If one of the .c files changes, I need to regenerate the .o file corresponding to that particular C file, and then I need to just call the linker to combine all the .o files together. So rather than having 1001 different steps to be performed, right, so 1000 steps for compilation plus 1 for linking, I now have two steps, one compilation and one linking with all the .os that are already present, right. The linking might potentially take time because after all it is still linking 1000 different objects together. That part is not so easy to solve because I finally need to create a new executable, but that typically takes much less time than compiling 1000 files. Now, as I mentioned, you want to recompile a file only if it has changed. Now, how do we detect if a file has changed? You could keep track of the modification time of the file, and the operating system usually tracks that pretty well. But then you need to write a script which basically says, okay, check the date of modification or the time of modification of each .c file, compare it with the time of modification or time of creation of the .o file, find out which one was more recent. If the .c was modified more recently, then regenerate the .o file and so on, right. It turns out that there is one command or one program that pretty much handles all of this behind the scenes for us quite nicely, and it's called the make command. And what make does is it basically allows us to track file changes, right. You can set targets which basically specify how I want different parts of my code to get compiled. It will handle the individual compilation stages all at once, and it will recompile only as needed, right. So, it will check the dates of modifications, and it will also check dependencies. If you specify somewhere that arith.c depends on arith.h, then anytime I modify arith.h, it will go back and recompile arith.c, which also means you have to be a little careful about how you specify these dependencies. It's not always obvious how, the sort of easy thing to do is just say that everything depends on everything else and you are back to square one. Any change in one place, you recompile everything. So that's not helpful. But if you know, for example, that the arith.c depends only on math and certain kinds of functions like that, whereas there is another string processing.c file which does not have any kind of math operations in it, then it need not depend on arith.h. Okay. So this allows us to do parallel compilation. Make is actually a lot more general than that. It is not restricted to C programs. It in general looks at the targets that you want to generate or compile or create, looks at the steps that are involved in them, and automatically in some sense figures out what are the things that need to be recompiled or regenerated, and does only the minimum amount of work required for achieving that purpose, right. So in general this is sort of a nice thing to do, and we'll take a very brief look at it in the context of how Replit does it, but actually understanding how make works is a significantly more complex problem on its own. So if you go and look at the files that are present in Replit, you will actually notice that you don't really get to see the make file, for example, right. There are some files that are missing out here. If I go onto the shell on this side and I type ls, I find that there is a file called make file. There is also another file called replit.nix, right, and there are some of these .o files, all of which got hidden out here, right. The Replit browser, file browser, is not showing those things to you, right. And the reason is, of course, quite simple. It basically says it's hiding those files. So if we ask it to show the hidden files, now suddenly a lot more things pop up, including a file called make file. There are a couple of things that show up as config files, which it's probably best to leave alone, right. You don't want to change that as long as you are using Replit. These are also completely meaningless outside of Replit, so make of that what you will, right. So the make file looks like this, right. You can see a lot of these words saying all colon, then there is something else colon, main debug colon, and so on, right. Each of these is what's called a target. So main, for example, is a target, and what we can do is there is some way by which the make file knows how to create a program called main. Clean is also a target. The interesting thing is it doesn't actually create a file called clean, because if you look at the target clean, what it does is it just runs this command rm-f, which is forcefully remove any file called main or any file called main-debug. So if I go here and I type make clean, it looks at the make file sees that yes, there is a target called clean. What should I do for that target? Go ahead and run this command, okay, and it removed. So it tells you that it actually ran that command out here, and if I now do ls, I find that my main, this file that was over here, has now disappeared, but other things like my abc, my a.out and so on did not disappear, even though they were created by me, right? The point is the make clean doesn't know anything about the other files that I created. So let me manually remove those. And now it looks a lot cleaner, right? What I can do is, so now that I have removed the .o files as well as the abc, a.out and so on, the other files that I had created, I find that I am pretty much back to the starting point, right? I have an arith.c, arith.h, this broken folder, just ignore it for now. There is a comp.sh that I used in order to demonstrate how I could manually compile. There is a main.c which actually contains the code that I want, and of course this make file that we are seeing on the left hand side over here. Replit.nix, as I said, is a configuration file, ignore it for the time being. So now what this basically tells us is that if I want to go ahead and now compile something, I could try typing something like make abc, and the problem is immediately the make file says no rule to make target abc, stop. It doesn't know how to proceed at this point, okay. So only the targets that have been defined here, clean is one of them, main debug is another, main is another, and all is another, right. You will see that main has some things out here on the right hand side. These are called the dependencies of main, right, and that in turn is some kind of an environment variable. Replit is being a little clever out here. It finds all files with the name star.c that are present in your folder and decides that those are source files. It also finds all header files and decides that those are header files, and that your main depends on all source files and all header files. Now in general that's not really true, as I told you, right? You might have a scenario where that's not really the case. So this is probably not the most efficient kind of make file in general to use. It's a good sort of shortcut for the case where you are experimenting with code and you just basically wanted to recompile all the files, recompile main anytime any of the files anywhere changes. But in general you should probably be a bit more selective in terms of how you specify the dependencies. Now the point is, what this says is, at the end of the day, if I run through these scripts, what I will find is that the sources variable will contain the names main.c and arith.c, and headers will contain the name arith.h. What is going to happen is, anytime any of these things changes, it will go in there, compile all of these files, create the .os, but it will put them somewhere specific, and it will finally create this $@ which basically refers to the name out here, main. So if I type make main, it goes ahead and it runs some kind of a compilation process and finally creates this file called main. And of course I can run it, it behaves exactly the same as before. Now the interesting thing is, what happens if I type make main again? It says it's up to date. I did not change any of the files, it's not going to recompile, right? So this is where the benefits of make basically come into the picture, right? And one last thing with regard to how make works, you will see that all over here is basically what we would call a default target, right? It doesn't really tell you what to do because there's nothing on the second line after all. All that it says is, if I ask to make all, make main, make sure that main exists, right? So if I now type make, it says nothing to be done for all because it's actually trying to create the all target. The all target depends on the main target. The main target already exists and there is nothing else that I need to do. If the main target did not exist, so for example if I remove this main file and type make, it basically creates main and then says, yeah, I am done. I don't have anything else to do at this point. Okay. So make is a very powerful way of organizing or building large pieces of code, right? For now, we are working with relatively small pieces of code, so we don't really care too much about this. We could just compile them by hand. But generally, for anything that is non-trivial, you need to have some kind of a build system. Make is pretty much one of the oldest that exists. There are other more recent ones that are used in different kinds of projects that have some better features, automatic parallelization of compilation and so on, which are in some ways considered superior to Make, but the point is Make is pretty much available everywhere on any Linux type of system, which is why it is still very popular, right? And it's always good to know the basics of how it works.